Okay, so I could show you in the code how to do this, but again, I think it's important if you get it from a general point of view. So let's say you have a surface, any surface, and that's the nice thing about it. It could be any surface. It doesn't have to be a flat one. The example was with a flat one, but it could be anything, right? And you have your free surface at some point. So any little surface, let's say this guy has position and depth, has a little area, and has these components, right? Which indicate the normal of the surface, right? So just to summarize, for each of these, and you had this in a table, right? So it was a data frame. So you had 0, 1, 2, 3, and all elements. And here you have all these columns, right? So for instance, if you look at this row, this would be the x position, y position, z position, the area, the depth, and whatever for the element 1, which could be, I don't know, this one, and this could be 2, 3. It doesn't really matter which one is which, but you had them all in rows. And then you had columns. So this column z was the z value for all of the elements, right? So basically, again, the pressure in each of these elements, the pressure could be gamma times h, and h, of course, in your code, it could be something like gamma times, I think it was called geometry of h, or depth. I don't recall how it was called, but it's the same idea, right? This could be the pressure, and actually you were given the hints. First compute the pressure, then compute. Let me just have it. Yeah, compute the pressure, then compute the total force per cell. Well, that would be uh, pressure times the area, which was given, then distribute on components. Okay, so that would be dfx, dfy, and dfz. Good. That this is going to be only df dot um, ijk. Maybe this step was a bit tricky, but this was in your lecture. Basically, what this is saying is, okay, the total force is just the pressure times the area, but where is this pointing for? And this vector just gives, this is a unitary vector, right? So it has a length of 1. So when you do the dot product with in this case, this is a value, well, then you're distributing these values in these directions. So if this guy is pointing upwards, and actually I think it was minus, because it has to point in the other direction. Uh, so yeah, maybe this part was a bit tricky. And then the total force in X is just going to be the sum, that sum in all of X's. And this is actually, this is the approximation of the integration, dfx. It's just summing, right? And this is, to me, the cool thing about this. You don't need to know the integral of the cosine or whatever. If you are given the geometry, you can just compute the pressure at each element, then compute the force at each element, then project the force in the corresponding vector, which only depend on the direction the element is looking at. And then the total force is just the sum, right? And of course, F, total F is going to be is going to be Fx, Fy, Fz, and the magnitude of F, all right? The magnitude of F is just each of these square, right? Plus Fy square plus Fz square. That's just a magnitude. But I think in the exercise, the magnitude didn't matter much. I mean, we were looking at where this was looking for. And the cool thing is that you get the vector. So for instance, if you did this right in your flat surface, you would obtain something like uh, I think it was 0 in x, and then a certain force in y, and then 0 in z, or these were switched around. I don't recall, because the normal, yeah, just like that, because the normal force only had components in j for the wall, for the flat surface. Now that was not the case for the vessel, for the ship. But before getting there, how do you compute the position? Well, the position is, as some people said to me, I know this equation, right? So it's y at the center of gravity times the moment of inertia divided by area times iz. How do I apply this? How do I apply this in this mesh-like approach? Of course, you can't apply it directly, right? Because this is the result of integrating this. So how do you apply it? I've told you this in class. Basically, basically, let me just close my Outlook because I'm getting notifications. Okay, basically, this is like this. Let's say you have yp times fy, and this has to be uh, equal to the sum of ypi dfy df. Yeah, because the absolute value, this is a sum of torques. So the total value times its arm has to be the same as the sum of the little ones. So basically, iy is just the sum of I. I'm gonna put just iy times dfy, uh, and for each divided by fy total. So for each cell, you had this because you computed this, and you had this because it was given. So all you had to do was multiply them, sum them, and then divide them by this guy. And you could do the same, and this is to me the cool part. You should do the same for x and for z. Maybe this was a bit tricky, but it's nothing you shouldn't know. And this is exactly why I am a bit skeptical about remembering equations without really understanding where they come from, right? I've also told you this only applies, to nice common geometric shapes. But if you have, let's say, a dam which looks something like that, you can't really compute this the moment of inertia. Well, actually, the moment of inertia, it is something of an integration of this area. So why don't you just go ahead and integrate the position? So I don't know if that's clear for everyone. I haven't checked what you have done. Uh, maybe some people uh, got it right. I don't know. But that was the way to compute this. Okay, is that clear, or should you want another explanation? Okay, I'm gonna assume it's either super clear or you didn't understand anything. It's super hard for me to get your reactions, but yeah. So it's just uh, it's just doing the integration, but numerically rather than analytically. And then the cool thing, I think, is that you were given one example, and you were actually given the values that you should arrive to. But if you do this right, then you can apply it to anything. So for instance, you were asked to apply this to a vessel, to a ship that had a certain geometry. I don't know if you could look at this geometry, but the cool thing is that uh, the geometry was fully underwater, so the free surface was just here. So if you compute the force on all of the hull, on all of the faces of this ship, you actually get directly the buoyancy force. So if you apply your little function, I don't recall what it was like, but it was a function of geometry. This thing will give you the force, the total force, which in this case it will only have a large component upward. And this I think is cool because, as you can see, if you look this from the top, basically it's like that. So you had a lot of components like this, but all of the lateral ones just get canceled out, and only the vertical survive. So once you apply this has almost 0, 0, then a certain value here, f, uh, and that value was equal to the buoyancy. Okay, and you were asked to express this as tons, so you have to pass them from newton to tons, and you were asked about the weight of the ship, right? So you should know this is, let's say, buoyancy force. Well, what are the forces going down? It's just the weight of this ship plus the cargo. I'm going to call it dwt. So this should be equal, and you should know this, and this was given, so you could solve the weight of the ship. And that's the weight of the ship without cargo, empty, let's say. So if you had write your function, you should get this more or less easily. If you didn't, but you explain your reasoning, then should be you should get some points too. Did anyone did the bonus part, or was it too hard? No one. I'm gonna assume no one. Okay. The cool part is that later on, all most of your work is just defining this geometry, just as when you do integrate something. So let's say you had a so let's say you had a let's say an sphere. Let's assume this is something of an sphere. Then if you were able to describe this infinitesimal uh, area, you should be able to integrate this directly. And this is, I don't recall it exactly, but it's something like d phi times sine d theta times r square, something like that. It's not that there is a sign somewhere, but I don't know it exactly. But you could have done it for a cylinder, or for a cube. For a cube was actually quite easy, right? Because you only need to keep in mind the directions of the areas, but it's always the same little areas. I don't know, 10 by 10, but you only need to have 6 of those sides, pointing to the right side. Maybe this could have been easy, and you could have, if you apply this function, this should have given you the buoyancy force, the total buoyancy force. Okay. Anyway, um, so that was about it. That was about the homework. It was really to test your knowledge on um, on pressure forces, pressure static forces, before the test. And as I was being asked, we have a test this Friday, and the test is going to cover only chapter 1 and chapter 2. So would you like if we do a very brief, shallow recap of those chapters before we dig into that? Since you're doing this at home and nobody is stopping you for having, the books or Wikipedia or whatever source you have, I'm not going to give you the equations. For instance, the equation I just wrote down, like y p is yc I I think YC area. I think it's this one. I'm almost sure. I don't know it by heart. And since you can have it, just write it down in a paper sheet or have it at hand. I'm not going to give you this. And also the inertias, you must know for a square, for instance, the inertia is BH cubed divided by 12. This is B, this is H. If it's rotating against this axis. If it rotates against this axis, you should know this. This is B cube divided by 12. Does everyone know this? You should know this from algebra or from uh, I don't know exactly from which course, but you should be familiar with this. Okay, and if you're not, you are allowed to to have a paper sheet with these kind of things. And like I said, I mean, you're doing this test online, so if you want the moment of inertia of a rectangle, it's pretty easy to Google it. So all I'm saying here is that I'm not going to give you these equations. Okay, this is pretty much what you should know by coming here. And the moment of inertia, we're not going to ask you anything pretty much more complicated than this, probably. This is not a geometry class, so I don't mind if you know how to compute the moment of inertia of a cube or whatever. Okay, so what we've seen, introduction. I'm gonna need a little feedback here. What did we see in the introduction? What do you recall? We talk about characteristics of fluids, right? So we talk about density, uh, specific gravity, um, the units that they should have, right? We talk about um, we talk about surface tension, sigma. Surface tension, what are the units of surface tension? Newtons per meter. Excellent. Newtons per meter. We'll talk about viscosity. This is a key concept of introduction chapter, viscosity, right? And what did we say about viscosity? Viscosity is the is the let's say is the opposition of the flow to drain, to deform, to constantly deform, right? And we talk about there are many ways in which fluids can be viscous, but the top way is a Newtonian way, right? In which the shear stress is proportional to the shear strain, and the constant of proportionality is the viscosity, right? This is a key concept. We talk about porosity too. That was just more of an example. Um, yeah, so this chapter was mostly about definitions, and then the most working definition is viscosity. And we talk about, remember, if this was tau and this it was the shear strain. For everyone, is this clear? If I say shear stress, you know what we're talking about, or the units of shear stress, or the units of shear strain. Maybe you don't have it, maybe you don't know it by heart, but you should be able to get these units, right? And basically we said, okay, if you plot this, you might get, if you get a line, then it's a Newtonian one, Newtonian, which is most working fluid. It could be something like that, something like that, something like that, right? Okay, that was pretty much introduction. Anyone is missing something from the introduction? I'm doing this by memory, so this is by no means extensive. You should go and read about these chapters. Then statics. What did we say about statics? That there are no velocities and and everywhere, and therefore there are no shear strain. I'm sorry, zero, and therefore there are no shear stresses. So the only forces you have are normal forces, which are pressures. So pressure is king in statics. And what did we say? We said that pressures don't change in the horizontal, and the pressures only change in the vertical. Do you recall how they change? Anyone? Gamma. Only due to gamma, only due to the specific weight. Because the only thing that creates pressure is the weight of the fluid. 20 years from now, this is the only thing you should remember from this course if you don't work in hydraulics later on. Right? And this is going to be useful in many other areas, not only in hydraulics. Okay, we said that. And then we said, um, well, anything in the water. I'm going to get to the details of the midterm later on. So give me a moment. So anything in the water is going to feel pressures, and they're going to feel forces, right? So if you have a flat surface, this flat surface has a certain pressure distribution. So these are pressures, and there is a total reaction force, just what we were talking about now. And the total reaction force is simply going to be the pressure at the center of gravity times the area. Do you know what this is? Why this is? I don't need you to remember this by heart, but I need you to understand why it is. So I'm going to say it again. I think I said it the other day, but maybe, I know this is new for you, so it gets confusing, but pressure varies linearly over an area, just like the same area. So since it varies linearly, the pressure at the center of gravity, this is the same as the average pressure over the area. This is the same as the integral of P uh, dA over the full area by definition, and you get to the pressure at the center of gravity. So it's representative of the mean average pressure all over the surface. That's why you can just compute this and apply it to the area. If you didn't have this, because pressure varies, I don't know, exponentially, like in a gas, for instance, uh, or your area is too complicated, then the right way to do this is just integrate the pressure on little areas. Okay, this should be clear. I'm gonna delete this and I'm gonna go to the left. And where is this pressure applied? Again, the pressure is applied in a point, oh, in a point such as the 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 distance with the distance times the force is equal to the sum of the little forces for their individual distances. This is by definition. And therefore, IP by definition is this integral divided by the total force. Uh, you can, in the book, it says, okay, on a flat surface that reaches the free surface, and you take this as y, right? You can do this, but you have to be aware of all of the things that you're assuming. For instance, this equation, yc plus this one, this assumed the y measured from the free surface, for instance. You should be pretty clear about that. Whereas this one, y you can measure it from wherever you want. It could be from the bottom up. It doesn't matter because this is general and this is a specific case. Okay, so you can use it, no problem, but you need to understand if you're able to use it. Like in the homework, you couldn't just directly use this. You had to actually go in and integrate stuff. So you probably have done this before, but if you have a plate, this is a free surface, this is your pressure distribution. Okay, the total force depends on P at the center, but where is this force applied? For instance, measured from the bottom. Does anyone know? Let's say this full thing is H, so PG is nothing more than gamma H half, right? But what value is this one? H small. This should be really, really easy. If you're I mean, you can say, well, I don't know this guy, so I have to compute this. That's a long way of thinking about this. The short way, no, nobody has a clue. H third, yes, H third. It's H third. This should be more or less straightforward because this point, H third, is actually the center of gravity of the pressure distribution, right? So it's a point such as uh, if you point this triangle over this one, and if you tip it over, you can actually balance it at that point. This should be straightforward. Now, if you have a plate and it's, I'm sorry about the sketches, they're pretty sketchy. But if it's here, you should realize that the pressure distribution now doesn't start at zero. So if this is your plate, now it can't be at 1/3, but it's going to be 1/2 here and 1/3 here, and you can compute the weighted average. Or you could apply this if you know how to apply it. Don't worry. But the straightforward way to think about why P is the, I think at least it works for me, is the center of gravity of the pressure distribution. Okay, and it's the same with X, though normally these kind of problems are going to be symmetric, so X is just the midpoint, but they could be, they don't have to be symmetric, right? So if not, you just have to do this very same but with X instead of Y's. Okay. What else did we see? We talk about buoyancy, which is nothing more than the integration of pressures over a body. So if you integrate all of the pressures, since these guys are larger, then the total net force is upward. That's the buoyant force, right? And we also said you could project, let's say this is a sphere. If you cut it this through a plane going like this, you would only see well, this is, yeah, this is sphere. You're going to see a circle. So if you know the area of the circle, you can compute the lateral force based on the projected area. You don't actually need to integrate this in a surface, but you can just project it into a flat area, right? And the same goes in the vertical. You only need the volume above, for instance, to know the full vertical force. We talk about that, and we also talk about floating bodies, right? Right? If you have a body that is floating, we said, well, it's going to float at such a distance as buoyancy force is gonna be equal to the weight, and there's gonna be a floating stability criteria, which is that the distance between the buoyancy point and the center of gravity has to be smaller than the moment of inertia of a certain plane divided by the volume of buoyancy. This is basically the distance between CC and the meta center. So if you have this block, you can try to rotate it like that, or you can try to rotate it like that. You're going to have different y's, and the smallest one is going to determine if this is stable or not. I think that's it. That's a summary of what we've seen. See, I'm being asked. Uh, yeah, I'm being asked about the projection. This is a bit. This is important. So let's take a minute. So if you have any surface, okay, I'm gonna try to draw this in 3D. So be patient with me. Let's say you have this 3D, and this is, we're gonna call, there is a convention, right? So this is X, Y, Z. And let's say you have free surface around here. I'm gonna draw the free surface. Okay, right? And you have a surface, whatever surface. I'm gonna draw it in red. So you have any surface. This is a small surface. That's the only, and it has an a vector. If you project this on each side, this is gonna be one area, whatever area. This is gonna be another area, whichever, and the same downward. Maybe this was not clear now, but if you thought about it and you're listening to me now, it should be clear now. So let's say this is delta area, and let's say this vector is n, which is like I said. Oh, I'm gonna write it. I'm gonna write it just farther away. So n is gonna be y, j, k, a unitary vector. Okay, so this was the trick. The area here, the area in X, is just dA times Y. The area here, dAy, is just dA times J, and the same here. dAz is dA times K. By definition. So if that, you can do the same with the forces, because the forces is only the pressure at this point times the area. So the projection of the forces is just multiplying this for the corresponding vector. And since these vectors are unitary, that means that if you sum them up, you know, in squared, then you're gonna get a value of 1. So this is the way in which you project the area, and this is why if you have a ball, for instance, or let's say not a ball, let's say a cylinder. I'm gonna try to draw a cylinder, but it's already cramped. If you have a cylinder here, on Y, you only are. I'm sorry, there's a lot here, but try to follow what I'm trying to say. On Y, you're only going to see a rectangle because that's the projection. and on X, you're only going to see an area. And actually, if you compute the pressure on half and multiply it by the area, you're going to get this force. And if you compute the pressure here and apply it by the area, you're going to get that force. And then you know that those forces are actually acting here, right? Is this clearer? I think this is very important. So if it's not clear, I'm willing to do it once more. Okay, this is, to me, this is key, all right, of this chapter. You should be able to compute forces on bodies, on floating bodies, on submerged bodies, on curved bodies, and you should be able to compute where the force is applied. Uh, you can remember the equation, or you can integrate this. You can decompose the surface. There's many ways when you can get the same valid result. You need to understand the physics of it. If there are no more questions about the summary, um, let me just yeah the let me go about the details of the exam. Basically, it's going to be there's going to be several small questions like true or false or multiple alternative selection. There are going to be a couple of questions in which you have to type down, let's say, a solution. Let's say you have to write down whatever F equals M times A. And I don't mind if if you write M X or M times, I don't mind. It's just text, right? As long as you can show what the equation that you need to write it is going to be okay. This is because multiple selection is good. I mean, you have to know, but there is also a lucky part of it, right? So you might not know and just get lucky. So there are going to be a couple of these kind of questions that you need to type down the result. And there's going to be one how do you say, one long or longer question. It's going to be quite heavy. Let's say a third of the exam, something like that. I haven't fully decided yet, but there's going to be one long question in which you're going to have to do some computations on a paper sheet on your own, and then upload it. If you have a scanner, you can scan it. If you have a picture, I mean your cell phone, there are applications that can take a picture and turn it into a PDF, so it will rectify it so it doesn't look uh, so scruffy.
Is it
If you don't have any of that, you can just take a picture. Yes.
gonna be question one, then two, then three, or could we do the whole thing like in this order? I mean, because like in some tests
Yeah.
you have
You're
to.
gonna you Yeah. I'm sorry. What?
No. That is it gonna be in order or?
No, the idea is that the questions are gonna appear to you randomly. So it might be that you get this long question as your first question, or as your last,
Okay, but
right?
we're gonna have to
So
first the one that we got first. We can't
no,
go back
the
to the first question after we're done with the first.
no, it's not gonna. Yeah, you're not gonna be able to see the previous answers, but
Right.
you're not going to need them. They're
Perfect.
gonna be independent questions.
Thanks.
Okay. And I'm being asked how long it will be. It's going to be 2 hours. I'm sorry. It's going to be a Friday evening. I know, but you can have your beers ready for when you're done. So we're gonna get together. I'm gonna send you a link. So we're gonna get together at 7:30, and we're gonna have a few moments to get together, talk about the details, and then the exam is going to start a few minutes after that. Um, so the key part is that you need to be able to turn in a picture or a PDF of of a paper sheet. You need to be able to do that. If you can't, for whatever reason, let me know now or soon, because it is important. Like I said, worst case, you can take a picture of it, and that should be enough. Um, okay, like give me a moment. Okay. Um, so yeah, before the break, is everything clear? Yeah, we're being asked if you have pautas from past semesters. I don't have any, but you have the book. The main source here is your book. So if you understand the book, you're gonna be able to do the questions. And you've been to the recitations, so it's gonna should be similar to that. Yeah, the book by Bonifacio is a book that I use. So you get, I think that you have it has more complicated exercises than you need. So if you can get your hands on it, that's great. I'm not gonna ask anything from it like directly, but I think it's a very good source if you want to exercise. Besides from that, recitations and what's on the book should be enough. I'm sorry, I'm being asked too much to ask to do the test in disorder. What do you mean by that, Roberto? Why do you need to go back? These are independent questions. So once you answer once, that's it. You need to realize that we are in this weird pandemic scenario, and we're all connected. You guys are connected with your friends, so the idea of you getting the questions randomly and not being able to look in back is so you don't copy. I think that's pretty clear. So you do have time enough to do the test. So just think very very carefully before submitting each question. Yeah, I understand, but you know it's a compromise from everyone. Unfortunately, I can't be. I don't want to be your police or your nanny. So I'm not gonna ask you to have your camera on you and looking at what you guys are doing. You're all grown ups, but we need to reduce the incentives to share information. So that's why. But there are no tricky questions. There is only one long question, the one you had to do on paper. All of the others should be pretty straightforward. Okay. Um, so that's it. I don't have any more material. So the book is a pretty good source of material, and what we've seen in classes. I mean, you've seen more. I've showed you more or less examples of structures or so yeah, have a look at the classes, have a look at the book, but I don't have previous tests. The non-PDF question is going to be theoretical. It's going to be a practical one. I mean, something like compute something, and explain how are you computing it. No, you have to. I mean, yeah, you can't just say, let's say if I say compute the weight of something, you can't just say 100 tons. That's not an answer, right? You have to say how you get to the 100 tons, just like a regular test. So it's a computation. You need to show how you're computing stuff. Okay. So we're gonna get together in a chat like this just before the test, so you can throw in any of these questions. Um, I know it can be stressing of this format, but it's the best we can do. So just to summarize, I know we should take a break. So let me just summarize. One long question. You're gonna have to have paper and a pencil and a way to upload whatever you do. Could be a photo. I don't. It doesn't have to be a PDF. It ideally, if you have a scanner, just PDF it. But if you don't have, just a picture will do. And the rest of the questions are gonna be self-contained, like multiple answer selection or true or false, stuff like that. Okay. So let's take 10 minutes break. I have 7:30, so at 7:40, I mean 5:40. See you in a bit. Okay. Great. Okay, are you guys there? Okay, so um, let's keep this recapitulation thing going on. Last week we talked about fluid kinematics. Yeah, 10 minutes left. Didn't we say 7:30? Oh, okay. Maybe, yeah, maybe I just read. Let's give it a moment, okay? Sorry, yes, thank you. I was mute. Okay, so I was saying we are talking about characteristic of flows. So we had steady flow versus unsteady. In steady flow, nothing changes with respect to time. Then you have uniform flow and non-uniform flow, and these are changes with respect to space. So uniform is no changes with respect to space. A typical example is the flow on a pipe, on a horizontal pipe. And then you have approaches to how you compute stuff. So you have Eulerian, which is on a fixed grid. So these are X and Y, for instance. And you have Lagrangian, which normally you follow the flow, right? And we talk about streamline. Over a streamline, you have that this holds true. The streamline is parallel to this vector dx, dy, dz, which is just a vector. The It's a differential path, let's say ds. Okay, and this was the core of what we saw last week. Basically, the acceleration. We said this, the acceleration has two parts: a local acceleration, which is actual change of the velocity field over time. Here, v is a vector, right? It has three components, and you have a convection term, and this might be different from other physics you've seen, but this is key to fluids. So you can have acceleration because the flow changes over space. A typical example is a waterfall, for instance. As you approach the waterfall, there is a change in space, and actually you start accelerating, or a contraction of flow. So if you have a big tube and then it flows into a smaller tube, you have a local acceleration in that change. That's due to this fella here. This is key. This is a key concept. And then we talk about continuity or conservation of mass, and we can express that in terms of density, in terms of rho. So basically, the conservation of mass says in a point you have local changes on mass or on density plus advection terms, right? And the advection term says, well, the mass that's being moved around has to be the same. You can't move around mass that is not there. And if you take, of course, if this is steady, then this is normally zero. But even if it's not steady, but rho is constant, if rho is constant, then this is also zero, right? And rho is constant, for instance, for water. So if rho is constant, you normally get to this equation, which is pretty elegant, I would say. It has to be zero, and this is just nabla times the velocity. Has to be zero. Okay, these were the key concepts last week. Okay, now we're gonna. You should have the slides of this week. It's the continuation of what we talked last week. So what we're gonna try to do now here is, okay, we know the acceleration, we know how mass is conserved, but we're gonna try to determine how energy or how momentum is conserved. Okay, so you have the slides, but I'm not going to show them to you because you can read them. But I'm going to try to show you the derivation that's in them. Okay, and for this, again, let's say we have a very small volume of fluid, and we want to determine the sum of forces over this little volume. Okay, as you know from Newton, the sum of forces has to be equal to the change in momentum. Like, this is by definition, right? And the change in momentum, if the mass is constant, this is just m times acceleration, right? In the case of our fluid, uh, since we're talking about a very small unit of fluid, the mass, uh, we need to compute the mass of a small unit. So the mass is going to be rho times the volume, this small volume, it has a small volume, times the acceleration, right? So this is by definition. And the question is, of course, is, well, we know this, we know the acceleration from the previous whiteboard, but what are the forces acting on a small body volume? Okay, and you can see the slides, but basically there's two forces. Okay, there are body forces, which are due to the general acceleration field. A typical body force is gravity. So gravity is one of them. And you have surface forces. Does anyone have an example of surface forces? Okay, a buoyant force, but what causes a buoyant force? So you have basically pressures. What other? Yeah, weight. Yeah, this is a good. Weight is a body force. So G creates a weight. So weight is right here. So weight is a body force, right? And a surface force. Let me just draw it a bit. So if you have a small volume, you're gonna have a body force, and you're going to have surface forces, and surface forces act on the surface. So you might have one normal thing, and you can have also tangential forces. So this could be a pressure, and this could be uh, shear stress. You could have surface tension, which is also it's not a surface force because it depends on the length, but yeah, it could act like here. So we're not going to be concerned about that now. So basically, it's pressures and shear stresses. Stresses. So stresses are forces per unit area. Okay. So these are the forces that go in here, and as you mentioned, we should consider here the body and the pressures and the shear stresses. These are the three forces, the three main forces that we're going to consider. However, if you recall this little guy here, the shear stress depends on mu and the deformation rate, the shear strain, right? Normally, if I don't know if you had a look, but the units of this, the units of mu are pretty small compared to G, for instance. These are pretty small. These are order of magnitude smaller. So these shear stresses are normally much lower, much smaller than the pressure. Okay, the shear stresses had to do with the viscosity effect, and all of you have swum in water, and water is not pretty viscous, right? It's not like oil or like honey. Those are viscous stuff, or like petrol or stuff like that. Water is not very viscous. So we can say that the shear stresses, we can say, well, they're just so small, so we're not going to consider them. Okay. Why is this? Because this lets us have a simplified approach to this balance, to this force balance. We're trying to solve this. We're trying to represent how momentum is conserved, and the viscous forces are a bit of a headache because they are hard to solve. So we're going to say now, well, these are just too small. We can neglect them for now, and we're gonna do just that. So we're gonna keep only body forces. In most cases, this is just gravity. But if you are in a how it's called, in a centrifuge, and you're rotating like that, you're going to have an acceleration down and acceleration, a lateral acceleration, right? Uh, so that's a body force too. But we're not going for now. Let's say body forces are only due to weight, and we're only going to assume pressures and shear stresses. We're going to assume they're very very small. Okay. Uh, if we are assuming this, we're assuming that the flow is not very viscous, so it's non-viscous or frictionless. It doesn't have friction because viscosity has to do with friction and with opposition to flow. So we're going to assume that the flow is not very viscous. The fluid is not very viscous. Okay, so if we try to rewrite this, we get that rho times the volume times the acceleration has to be equal to uh, the body forces. We're going to call F body uh, plus the surface forces. Okay, and the body forces are going to be just going to be the volume times rho times g, and the surface forces are going to be minus the volume times the gradient of pressures. If you recall, when we computed buoyancy, we said that buoyancy is created because there is a gradient of pressures in the body. So this is all it's saying is, okay, if you compute the gradient of pressure in a certain body, multiply it by the volume, you're going to get the force. And in this case, it's acting against the direction of g. Okay. So this is our starting point. We could have here, uh, let's say the shear stresses, and then we would have here another term that we will see later on. But for now, we're going to say this is just very small, which is normally the case. Okay, any questions so far? Yeah, Fs are surface forces, and these are body forces. And these are, well, these are, let's say, these are normal surface forces, and these are shear surface forces. But these we're saying are zero. And we also know that the acceleration is we know the expression for the acceleration, right? So what we can do is here is that we can remove the excess. I mean, remove the volumes because it's everywhere, and we can get rho is the total acceleration, which we said is the local acceleration plus the advective terms, which you can write them in many ways, but this is a typical one. Okay, and this has to be equal to rho g minus the gradient of pressures. Great. Now, the gradient of pressures, it's also a vector, and g is also a vector. If you, g, not rho, g is also a vector. So this is a vectorial form, right? And we could separate by component. So let me just do that. So we get in x, we get rho times du dt times u du dx times v u y minus it has to be dp at dx. Okay, and you can do the same for y and for c. I'm not gonna write y because it's just the same. For c, it changes a bit. I mean, doesn't change that much, and you can see this on the slides. I'm sorry. This is u. Again, like I told you last time, so this is going to be rho z minus the ppd. Like I told you the last time, these are the terms. This is a nonlinear term. This is a nonlinear term. These are the terms that make these equations hard to solve. Okay, and I'm just gonna go ahead and write this here just for completitude. Okay, because you see, this is the y. Okay, here are two important things. Normally, in Earth, this is zero, this is zero, right? So basically, you have uh, the accelerations in each direction multiplied by rho. It has to be equal to your uh, general field of force, which is normally just gravity, minus the gradient in pressure. When we had static forces, we said that these two were zero, remember? This used to be zero, this used to be zero. That's not the case anymore. These are not zero. So pressure changes horizontally and it changes vertically. Okay, so this complicates stuff. And also, you have these nonlinear terms, and this is the other one, which make these equations pretty hard to solve. These are called Euler equations. Euler equations. And these represent, again, non-viscous flow, non-viscous fluid. Okay. Um, this is sometimes called ideal fluid because it doesn't have viscosity and therefore it doesn't have turbulence. So it's just kind of ideal. Uh, but nonetheless, these are pretty useful, pretty commonly used equations. And actually, we're going to use them. We're gonna show you about a specific way in which you can solve this to make these equations useful. Otherwise, it's just pretty hard. Any questions so far? Okay, what we're gonna do now, it's a bit tricky, but I think it's interesting. We're going to assume that we did this based on a small volume, right? So we're going to assume that you have a certain flow and that your small volume is flowing along this flow. So you're going to have, let's say, a certain trajectory or a certain how we call it a streamline. Okay. So the velocity of this little cube is just normal. So the velocity uh, times ds is zero. Is parallel to the streamline. Okay. We're going to assume that, and we're going to assume steady state. Okay. Why steady state? Because, yeah, non-steady state is just too complicated. So if Euler equations, we said we add them steady state, that means this guy is zero, this guy is zero, and this guy is zero. Okay. And we already saw that these two guys were zero. So we still have a pretty complicated bunch of equations, but we can do a little trick. And the trick is this one: if we are in a on a streamline, we're going to have that dx over u is equal to dy over, sorry, over v equal to dz over w, right? Okay, so let's keep that in mind. I'm not going to show you for every equation, but let's follow what's on the slides, and let's take the equation on z or z. So the trick here is we're going to have this equation, and we're going to multiply it by dc. This doesn't look right. We're going to multiply this by dc, okay, with all the simplifications we already did. So we're going to get rho, just like before, u times dw dx plus v dw dy plus w dw dz. And we're going to multiply this by dz. And this is going to be, okay, so we're here on Earth, so g is negative. So this is going to be minus rho g, just g, minus times dz, because we're multiplying everything by dz, minus dp dz times dz. Okay, just keep in mind that these are derivatives, and this is an infinitesimal element. It's pretty much the same, but it's not exactly the same. Okay, and if we're on a streamline, here you can see, for instance, uh, let's focus on this guy. Here you can see, let me just draw this, I mean delete this. Here you can see that v times dz is going to be equal to w times dy, right? And u times dz is going to be equal to w times dx, right? And why is that important? Because when we multiply this, we're going to multiply dz times v, well, times this guy too, but times this, okay? But dz times u is here, is also w times dx. So we can get directly, this is just w dx dw dx. And this one here is going to be dzv, and dzv is w dy dw dy plus w dz times dw dz, right? Minus rho g dz minus dp dz dz. Okay, that was clear. Okay, and this guy, by definition, by rule of thumb, but I mean by rule of by the chain rule, this is just the full derivative of dw. If we take the omegas, I mean the w's out, so we can solve this like we can put this in a summary. I'm gonna delete just the lower part because it's just using too much space. So the first part is just rho omega, because I mean w, because we have w everywhere, and the rest one you see is the partial derivative with respect to x, and then times the x, the partial derivative with respect to y, and then dy. the same. So this is just dw. So this is just equal to minus rho g dz minus dp dz. Okay, I'm getting a comment. Is minus rho dz. Yeah, I think I have minus everywhere. Just minus. Yes, minus 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 rho g dz. Yes, and dt. Where the yeah, yeah, yeah. I'm sorry. It's just my handwriting is it's it's terrible. So there are no dt's because we said is this is stationary, so no time, right? This is dz. So you can do it on your own because the rest is pretty much the same. But what you get here for the other equations is just analogous. Is rho u du is equal to, well, 0 minus dp this I'm sorry, dx dx, and rho v dv equals 0 minus dp dy dy. Okay, so this is much easier to show, right? So we should be able to integrate this. Okay, so bear with me this couple of minutes because there's one small change. There's one more step that we need to do. And what we're gonna do now is that we're gonna sum these three equations. Okay, and what we're gonna get is we're gonna get rho v times dv as a vector. It's going to be equal to minus dp dx dx plus dp dy dy plus dp dz dz minus rho g dz. And if you were paying attention, this is just differential pressure. This is just dp, just like in the step before. Okay, so we get to a very nice, small, concise equation, elegant if you want. So we get to this. I'm sorry, I'm just deleting everything, but I mean you have the slides to where it's nicely put, but you get to this. It's just equal to minus dp, so we can move this here, plus dp, and we can move this other guy here too. Rho g dz is equals 0. Okay, and if now we integrate this, the integral of v dv is just rho v squared divided by 2 plus the integral of that is just the pressure, and the integral of that is just z. So rho g z equals a constant, whatever, right? And we can, you know, this is rho and this is rho, so we can divide by rho, but just by convention, what we normally have is this one. If we divide by gamma, we get 2g times pressure divided by gamma plus z. This is constant. And this, my fellow students, this is called the Bernoulli equation. Earlier, I said that if you had to remember something, it was something I said. I don't remember what it was, but if you're really going to remember something, it's this equation from this course. So what this does the Bernoulli equation says? It says, give me a second. Let me just delete everything. The Bernoulli equation says that along a streamline, this quantity is maintained, is constant. And what does this say? It says that uh, the vertical position, you can think of it as potential energy. The pressure, you can think of it, well, as pressure, so it's a kind of energy, and this is a measure of kinetic energy. This is pressure. So along a streamline, the sum of kinetic potential and pressure energy is maintained, is constant. Okay. So remember, in the static case, v was always zero, so this was always zero, and you would have this, that the change in pressure is just the change in z times gamma. Let me just put it more clearly. Normally, what you would do is you are going to say the pressure at the velocity at one point plus the pressure at one point plus the elevation at one point has to be equal to the velocity at another point plus the pressure at this other point plus uh, the next elevation. Okay, as long as these 2 points are connected by a streamline. That's the tricky part. Okay, so this is a very common equation. It's very useful, but you have to keep in mind the assumptions we use. So anyone, just to know that I'm not talking alone, what assumptions have we used that you can uh, say? This is pretty important. I'm gonna give you a hint. It's four assumptions we have used. Well, it's in the slides. You can also watch it. I'm assuming you have the slides there. So yeah, steady flow. This is that one is important. So no, but in practice, what we're gonna say is that it's almost steady, that it doesn't change that much or doesn't change that rapidly. That's gonna be the key. We said inviscid, inviscid. Maybe I wrote down terribly. Inviscid or ideal fluid. Okay. We said streamline, and we said incompressible. Incompressible. This was on the acceleration part. Okay. So we said it was incompressible. So this is not true for air, for instance. If air goes through a too large change in pressures, then you can't use the Bernoulli equation. But the Bernoulli equation, you can use it on water flowing, not changing very much on steady flow, because water is almost ideal, but you have to use it over streamlines. Okay. This is a key concept of the course, and I think the derivation is pretty nice, so that's why I took a time to show it to you. And now let me show you. This is a classical example too. Is as classical as you get it. Let's say you have a tank. Let's do this example and then we take a break. Okay. Let's say you have a tank. You probably have done this before. So you have a tank or a bottle and it's filled with water up until here. Okay. And let's say you have a small hole in the tank. So water is flowing here. Okay. And the question is, what's the velocity of this hole? Okay. And let's assume this hole it's at a depth h. So what's the velocity of the hole? First of all, do these four assumptions hold in this case? Are they true if you try to analyze this scenario? What do you think? Yes, the short answer is yes. So the first thing we should do is, okay, we should follow a streamline, right? So let's say, and here you have to be a bit clever on your streamline. So it is possible that a streamline comes from here to here and then out. Yeah, it could be. But are these 2 points pretty useful? Well, that's another story. Normally, what we will do is that we're gonna say that we start here, and you have a streamline that goes like that, and we're gonna call this one and this two. Okay, so let's do this. Um, I'm gonna delete this so I can have the whiteboard back. So right here at the top of the reservoir, you're going to have. Uh, Let me just write down the equation. Okay, so it's this one, and this is gonna be constant. Okay, what's pressure? What's the pressure going to be at the free surface? What's the value of pressure? Zero. We can always assume relative pressure. So this is going to be zero. What's the value of Z? Realize that it doesn't matter. Yeah, we got a question mark. It doesn't matter where you put your reference level. I mean, could be here, could be here. In our case, what really matters is the difference. So we're normally going to call this delta H. Okay. So let's say, for the sake of the argument, that our reference is here, just at the same level of the hole. So Z at the top of the reservoir is just delta H. And the velocity, what's going to be the velocity here? That's a bit trickier. Zero. Yeah. So you should know that you have water going out here at a certain flow. So we're gonna call this flow Q, and we're gonna say it's V, which is what we want to know, times a certain area that we don't know, an area of the hole. And the reservoir has another area. We're gonna call it area naught. Okay. So as water goes out, of course, the level is going to be dropping, right? It's going to be coming down at a certain velocity. And that velocity is going to be such that the flow here is going to be a certain velocity times, let me just call this area 1, because, yeah, I already used that one. So V1 times area 1, right? And we want to know V2. So by continuity, Q1, this is Q2, Q1. Q1 has to be equal to Q2, right? So V1 times area 1 has to be equal to V2 times area 2. So V1 is going to be V2 times area 2 divided by area 1. But here's the trick, and this is a common trick. Area 1 is way larger than area 2. The area of this reservoir. This could be, the El Yeso Dam or something. And this is going to be a centimeter. So this value is going to be way, way smaller than 1. Very, very small. So V1 for practical matters is almost 0. So we can assume this is 0. Please realize that it's not 0 in reality, but in practice we can assume it's 0. Okay, so if this is 0, then all the energy we have left is just delta H. So let me just write this formally. So let's call this the Bernoulli at 1. So the Bernoulli at 1 is just going to be delta H, right? And the Bernoulli at 2 is going to be, okay, let's do the same thing. V2 divided by 2G times pressure 2 divided by gamma times Z. We're putting our reference level here. So in this case, Z is 0. But how much is pressure 2? Well, pressure 2 is just delta H times gamma, right? So you see the pressure divided by gamma gives you just yeah, exactly. The pressure divided by gamma gives you a length, right? So the pressure here, okay, so V2 is gonna be V2 squared divided by 2G times delta G, delta H. All right. And this has to be equal to V1. I feel like I'm missing something. Give me a second. Okay, well, if these two are equal, this is just delta H, but then I'm missing the delta H. So I'm doing something wrong. Anyone can spot it. Okay, in the meantime, I'm being asked what happens if A1 is not big enough to assume. Then in that case, the velocity here is not zero. You can assume it's zero. Okay, I'm doing something wrong here, but I can't see it. But I know that the velocity should be 2 g delta H. Um, but I'm missing something. So I'm a bit blocked now, but I'm gonna look it later on and coming back to you. Um, because I'm being a bit messy now. But the velocity is going to be proportional to delta H. Um, so actually, yeah, to the square of delta H. And this is why if you have a bottle and you put several holes, you normally what you get is that you have very small velocity here, a bit larger, and the lower larger velocities. Okay, and because the velocity depends only on this difference, only in delta H. Okay. Um, yeah, I might have messed up my reference level. So let's take 10 minutes, and I'm going to revisit this now, and at the when we return, I'm gonna have it cleaner. Okay, see you in a bit. Okay, are you guys back? I realized I did a mistake. I made a mistake, and it's actually it shows a bit that you need to be careful with this streamline approach. The mistake I made is the following: the first part is right. Right here, the velocity is zero, and pressure is zero because it's up to the atmosphere. So Z is just the position, the vertical position. But here at the hole, yeah, the pressure right here, pressure divided by gamma, is actually delta H inside the tank. But we're interested in the flow, and the flow it's outside the tank. So here pressure is just zero again, because here inside the tank actually your velocity is also zero. So this part I got confused. This is the right one, this is the wrong one. Actually, if you use delta H, you get to zero velocity. Okay, so if you take zero here, you only get the one. Here you take this one, and the difference is delta H. So again, you get what I was saying, but I was doing something wrong. So the velocity is only proportional to the root square of delta H. And this is a result that you're going to see often if you follow hydraulics. But this goes to show that you need to be very careful how you describe your streamlines. Okay. Okay. There are many applications we're going to have in the recitation this Thursday. We're going to talk about Bernoulli applications. This is really the core of the course. So this is something that we're going to see very often. So before we move on, any questions about this? It is important that you remember that this only applies to a streamline, and since this is conservation of energy or momentum, only applies if you don't have an addition of energy. So, for instance, if you have a pumping system, if you have a tube and you have a pump, and the pump will add power or energy to the system, then you cannot apply directly this. You have to take into account the energy being added to the system. We're gonna see a bit about that later, but you have to follow a streamline. It has to be stationary. It has to be inviscid flow, incompressible flow. So that means water, uh, and you can't have uh, an addition of energy. So the propeller of a ship, for instance, is an example where you do have addition of energy. If turbulence is too important, so then you can't assume that it is ideal flow, is an inviscid flow. But if you're far away from the boundaries and the viscous forces are small, then you can assume that you can use uh, the Bernoulli equation. Okay, any questions? Okay, before we move on, I forgot to comment something on the homework earlier. There was a problem. Some of you noted that the actual not homework notebook file was modified with part of the answers during the night, and this was partly my mistake. I mean, it was my mistake because I gave authorization to people to edit it. I didn't realize that I was doing that. So from now on, you really have to open these things from your Mi Wandes account. If you're opening from there, you don't need any special permission. But I had to do, to give permission to a couple of people during the weekend, and it was late, and I did it on my cell phone, so I didn't realize that I let people change the original homework file. So in order to avoid that, please sign in to your Mioandes Google account before opening this stuff. All of you have that account, so actually most of you are have been able to do it. So for the incoming homework, which is going to be in a few weeks, you should be able to. I won't grant permission outside with different accounts. Okay, so I don't mess up again. Anyway, the the answers that were there were not fully right. So if you had a pick and you copied it, just make sure that you copied it right. Um, anyway, so we move on. Do you have any questions? Okay, I'm gonna assume we're all good. Okay, we're gonna talk about an issue that can be a bit hard to understand physically. At least it was hard for me at the time, and um, it's about vorticity. Vorticity, let me just write it down. Vorticity is the property of a particle of fluid, a small particle of fluid, to be deformed. So let's say you have a particle of fluid. This particle of fluid might rotate and deform. So it could rotate and deform like that as it is flowing. Okay. Um, and vorticity, there is a mathematical way to compute it. So we're gonna get into that, and it might be important because uh, well, vorticity is complicated, but if we assume that the fluid is not rotating and therefore it has no vorticity, then we're going to have an additional tool to represent flows. We already have this Bernoulli equation, which is basically an integration of the Euler equations, which are pretty general. They only lack viscosity effects. But if we also assume the fluid has no vorticity, then we can represent it in a different way, which is a bit more general than the Bernoulli. Okay, so what we're going to do here is we're going to assume that here we have a certain velocity. At this point of this parcel of fluid, we have a certain velocity and u in v, okay? And we're going to assume that this is very small, so we can estimate the velocity here, the horizontal velocity here, going to be u times u at the y times delta y. And the same goes here with v. V here is going to be uh, v times dv at the x times delta x. Okay. Now, these two points in the slide, this is called O and this is called B, and this point is called A. These 2 points are moving with the flow, are moving to your right with velocity u, point O, and with velocity u times this in this point. So they had different velocities. So therefore, after a time, you're going to have a difference in x between them, and that difference is gonna the difference is this part. So the difference in x between these two is going to be just uh, just this part, du at the y times delta y, this time delta t. This is how much farther the point B is going to be located to the right than the point O. And the same is true for the point A. The point A is going to be much farther up or down than the point O by an amount of dv at dx times delta x times delta t. Okay. Now that's that position, and we also know. Let me just, maybe it wasn't clear enough, but this side is delta x, and this side is delta y, and this is delta x. So you can estimate the angular velocity of this side as the velocity of the top divided by the length. Okay, so the angular velocity, uh, this angular velocity, we're gonna call OB, is gonna be nothing more than the velocity of the top, u dy, sorry, times delta y times delta t divided by the arm, which is just delta y. So you can see that the delta y's cancel out, right? And I'm sorry, and this is will be, this is the limit. This is going to be equal to the limit of this divided by delta t, and delta t goes to 0. Okay, and you can see as this goes to 0, this is t. So in the limit, this tends to the u at the y. So the rotation around this of this side is the u at the y, and the rotation of this side conversely is going to be dv at dx. We're going to call this w, ao, and this is, well, this is omega, not really w, right? This is omega bo. Okay, but what we're doing here, this is, I have no idea what we're doing here. So we're trying to estimate how this little parcel of fluid is being deformed due to vorticity. Okay, and this side is moving with this angular velocity. I'm sorry, with this angular velocity. And this bottom side is moving with this angular velocity. So we're gonna say, okay, and the angular velocities on the plane, you can represent them as a vector going upwards, right? So what we're going to say is that omega around z is going to be the average of these two. It's going to be 1/2 of dv at dx, because this one is positive. This v at dx goes like that. So this, by the rule of thumb, this is up. This is up, and this one going down. This has to be negative, right? So minus du at dy. You can compute analogously the rest of this component. So the vorticity is actually a vector, right? So omega x, you can realize this, but omega x is just the w at the y minus the uh, the v at the z, and omega y is just half du dz minus the w dx. Okay, and this guy. So the vorticity looks a lot like a cross product. I don't know if you can see it. Maybe if you look at your algebra, um, if you look at your algebra, you can say by definition, the cross product of nabla times a velocity is going to produce very similar results to this. So what we're saying is that the total vorticity, we're going to call this half of this. And this guy here is called the curl. The curl in Spanish is rotor. The curl tells you how much the velocity field is rotating onto itself. Okay, so the vorticity is half the curl. Uh, no, I'm missing concepts here. Sorry. So yeah. So this is the vorticity, and the vorticity is, then is, yeah, the vorticity half the curl. Okay, so okay, but this is just too much mathematics. So what we're talking about here, uh, why is this important? It is important because if this is true, if I mean if this is zero, this means that the flow is not rotating, it is not creating swirls or eddies. If this is true, we can treat the flow as potential flow. Okay, and potential flow has the nice property that all the velocities can be expressed as the gradient of a certain potential function. Okay, so let me just uh, repeat that. So yeah, I made a mistake. So we had the vorticity is 2 times the rotation vector, which is the same as the curl. So what we said before is omega. Omega is just the rotation vector. So the vorticity is 2 times the rotation. This two is really not important for us because we're going to assume that this is zero. And if this is zero, then we can use potential flow. Okay. And what is potential flow? Let's say that we have a certain potential function. Potential function. If we have that the vorticity is zero, then we can express the velocities as the gradients with respect to each direction of the potential. So you can think as a field that has a certain potential function, and the velocity tells you where that potential is going down. Okay. So basically, this is saying if this is true, we're saying that the velocity, the velocity is equal to nabla this function. And since we're saying that nabla cross the velocity is zero, we have these two equations. Okay, and this is going to be useful to determine the potential. Now we also know that by continuity, nabla dot velocity has to be zero. Okay, but this is just nabla dot nabla phi. This is zero, and this equation is called a Laplacian equation, a Laplace equation. Okay, and why is important? Because a Laplace equation can be used to solve wave-like problems. It's an equation of transport, which is non-linear, but there are pretty useful ways in which we can approximate this. So to summarize, vorticity, or the rotation of a parcel of fluid, can be computed by the vorticity of the flow of the vector of the velocities. And the vorticity is nothing more than the curl of the vector field. If that vorticity is zero, meaning no vorticity, meaning the flow is not rotating, it's not creating swirls or eddies, then you can express the flow as a potential flow. And this has typical applications in wave-like flow. So basically, let's say you have a certain this is a top view. You have a certain channel, let's say. So this is a channel, and you have a cylinder here. Okay. Under potential flow, you can determine certain potential lines. You're going to look something like that. And the velocity field is going to be orthogonal to these lines by 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 definition. Okay. And you can compute the shape of these lines using this Laplace equation. This actually can be solved numerically pretty easily. I mean, you can do a nice approximation. So give me a second. So for instance, I'm going to switch here. So for instance, you could solve something like this. Something like this. And some lines here represent the potential lines, and some other lines represent the streamlines. There are parallel to the flow and parallel to the to the flow. So this is pretty simple stuff, but this can be used to to represent flow, at least simplified flows, without getting into the Bernoulli equation. This is not very used in practice because it's pretty simplified, but it can be useful. Like I said, it can be useful to have an idea, a feeling of how the flow is moving. Okay, so that was for today. Um, do you have any questions? Do you have any questions? What we talk about today? We did a review of what's going to be in the exam of Friday. We did a review of fluid kinematics, and we finished fluid kinematics actually. So this recitation on Thursday, we're going to see some velocities exercise at least, um, and we're going to start with the next unit. I think it's differential approach next Monday. So, any questions before we go? There's not going to be any quiz on Monday, okay? So just focus on the midterm, and yeah, we can rest this Monday, no worries. Okay, if there are no questions, good luck. Keep on studying, and if you come up with questions, just post them on the forum so everyone can read them and I can answer you there. Okay? Okay. Okay, bye. Cheers.